As part of Tool 1, you are expected to be able to describe how to prepare a standard solution, particularly with reference to the correct glassware which you would use in doing so. There are some prior key concepts that would be helpful for you to understand before you begin, primarily what is concentration. So just knowing that it's a quantitative measurement determined by the amount, which is in moles, or the mass, which is in grams, of solute, and the volume of the solution, which will be in decimeters cubed. I'll discuss this concept next. When it comes to discussing concentration, it's typically used to reflect how many moles are dissolved in a particular volume, which is almost always 1 decimeters cubed of a particular solution. And so the formula N is equal to C multiplied by V is used, where N represents the number of moles, C represents the concentration, and V represents the volume. Note that the units for volume are in decimeters cubed, and if it's given to you in centimeters cubed, you should almost always be converting it to decimeters cubed, and that just requires you to divide the value that you're given by 1000. However, the units of concentration can also be represented with grams per decimeters cubed. So the same way that we would calculate concentration by dividing N by V, and that gives us the units moles per decimeters cubed, we can do the same thing to determine mass per decimeters cubed, where I swap in the number of moles for the mass, and so my units are grams per decimeters cubed. A standard solution is one that we are absolutely sure of its concentration. We can divide standard solutions into two types, primary standards and secondary standards. Primary standards are very, very unreactive, and although secondary standards are also unreactive, comparatively speaking, they're just a little more reactive. Because they're very unreactive, primary standards then are extremely pure, and again, although secondary standards are quite pure, they're comparatively a little bit less pure. One of the things that makes primary standards so pure and unreactive is the fact that they're not hygroscopic. Hygroscopic means that it has an ability to absorb moisture from the atmosphere. Let's imagine if we have a solution and we need to be absolutely sure of the concentration of that solution. If that solution absorbs moisture from the atmosphere, that's going to dilute it slightly and alter the concentration. But a primary standard doesn't do this. That means that its concentration remains exactly as it was originally made. A secondary standard doesn't do that. It will absorb that little bit of moisture from the atmosphere, and as a result, it becomes slightly diluted. So primary standards then are the ones that we use to standardize other things, which means to check their concentration. Whereas a secondary standard is one that we would only use for a specific analytical experiment which has to have that particular chemical to react with. The point of a standard solution is for us to be able to use them in a titration so that we can link the number of moles that's in them in order to calculate the number of moles or concentration that's in another reagent. So it's very important for a standard solution to have an accurate concentration for a titration. In order to make a standard solution, there's a couple of steps that you follow. First, you make sure that the mass of the solute is really, really accurately measured. So you do this by using an analytical mass balance. This is just a mass balance that will measure to 3 decimal places, so it's very, very precise. Once you have it measured carefully, you'll dissolve it in a beaker with some water. And you'll use a stirring rod to make sure that this mixes completely. After you have it dissolved in a small amount of water, then you'll transfer it to a volumetric flask. You'll use a funnel to make sure that you don't accidentally lose any of the solution that you're trying to transfer. And at this point, what you should have is a small amount of the dissolved solute in the bottom of the volumetric flask. The next thing I want to do is make sure that any of the small little bits that would be in the bottom of the beaker or the funnel, that they also get transferred. Because remember, I want to be sure that every single bit, every piece of that mass makes its way into the volumetric flask. So I simply just rinse out my beaker and funnel a little bit more and transfer both of them to the volumetric flask. That's called the washings, sort of like the leftovers that would remain in the beaker and the funnel otherwise. At this point, my solution is probably a little bit higher up in my volumetric flask. The last thing I will do is make sure that I fill up to the mark on the volumetric flask with distilled or deionized water. While I'm doing this, I'll make sure that I continuously swirl it and mix it so that I get a completely homogeneous solution. When I'm done, I'll also stopper it and invert it a couple of times too. Invert just means turn it upside down. So like I can invert my pen here. So I invert it a couple of times, and that just makes sure that I have a completely homogeneous solution. A homogeneous solution is one which has uniform properties throughout. There are two main ways that IB could assess this concept in an exam. The first would be in a calculation where they ask you, for example, to calculate the mass of something required to prepare a standard solution. And the second is a description of the theoretical concept behind how do I actually make a standard solution and what pieces of equipment would I use to do so. Let's discuss an example of a calculation question. So you're asked to calculate the mass of solid oxalic acid crystals, which you're told are pure, in order to prepare 250 centimeters cubed of a particular concentration. The first thing that you would do is label what you know. So for example, you're given a volume and you know straight away you have to convert that into decimeters cubed, and you're also told the concentration that you're required to make. You know that you're given a volume and a concentration, so the first thing you're going to do is use N is equal to C multiplied by V to figure out exactly how many moles of oxalic acid you'd have to put in order to make that concentration. However, IB wants you to calculate a mass. So now that you have the moles, if you link that to the molar mass, which you can just calculate from the periodic table, you'll be able to determine the mass that's required. So using N is equal to M divided by MR, and the number of moles which you obtained in step 1, and the molar mass from the periodic table, you can calculate the mass of oxalic acid crystals which would be required. The second question we're going to discuss is an actual past IB question. This question is worth 2 marks. So again, if you want to pause this video and set a timer for 3 minutes, you can attempt this question before I discuss it. So you're asked to outline, giving your reasons, how a student could carefully prepare a 1 decimeters cubed solution from 4 grams of sodium hydroxide pellets. Things that the mark scheme focused on. They wanted you to mention about the pieces of equipment like the volumetric flask and the fact that it's important to mix it and to make sure that you fill up to the line or the 1 decimeters cubed mark of the volumetric flask with distilled or deionized water. Any 2 points from either the key procedural steps, the technique aspects, or the safety precautions were accepted. You'll notice that the key technique aspects were all discussed in that slide where I discussed how to prepare a standard solution, and most of the things that are key mark scheme points here I highlighted in pink at that time. So for example, doing things like using a balance that has at least 2 decimal places or at least is very precise, or an analytical balance. Making sure that you use a funnel to avoid the loss of solution, and making sure that you transfer the washings. Notice with the funnel, it's not enough to just say, use the funnel to transfer the solid. You have to specify that the point of the funnel is to make sure that you don't lose any of the solution when you're doing it. Safety precautions, as you know, alkalis are always corrosive, so just making sure that you would handle them with care. And also when you add something that's a very strong alkali like NaOH to water, it's a very exothermic reaction. So that means that it will be important to let the solution cool. One other thing the mark scheme noted as a safety precaution is the fact that they keep NaOH in a desiccator. That's how they store it. The desiccator is something that just prevents moisture from being in the air. So this mark scheme was actually quite generous, allowing 2 marks to be awarded from any of the categories, including 1 from each or 2 from the same category.